Good morning to everybody. I'm Tiriolo, and today I'm going to present a research concerning about the development of a receding horizon control strategy capable to solve obstacle avoidance problems for differential drive robots that are moving in static but a priori unknown environments. This presentation is so structured. First, a brief introduction to autonomous mobile robots will be shown. Then an approach to model differential drive robots will be proposed, followed by a depth description of the derived strategy. Finally, the benefits of such an approach are discussed by means of experimental results obtained using an IPAC2 differential drive robot. Autonomous mobile robots are increasingly present in industrial and service robotics, particularly because of their potential applications in environment hostile to humans, resulting in the reduction of human risks. In general, these robots are required to operate in uncertain environments, avoiding any obstacle occurrence along the path. The most required autonomous tasks are motion planning and motion control between some different post configurations. Despite the extensive research on this topic, it represents a challenge, specifically when limited computational resources and perception capabilities are considered. Things turn out to be more complicated when non-holonomic constraints are taken into account. Differential drive robot is a two-drive wheels vehicle, and it represents a typical example of a non-holonomic vehicle due to the perfect rolling constraints on the wheel's motion. It is possible to derive a kinematic model of differential drive in which the state vector represents the position of the center of mass of the robot and its orientation theta, while the inputs of the system are the angular velocity of the left and right wheels, respectively omega L and omega R. A unicycle robot is also a non-holonomic vehicle, but it consists of a single drive wheel. In this case, the inputs of the system are the linear and angular velocities of the robot v and omega. By resorting to an affine transformation, it is possible to recast differential drive inputs into the unicycle ones. This transformation depends on the geometrical parameters of the robot, such as the radius of the wheels and the length of the wheel's axis. To obtain a linear model of the robot, we resort to feedback linearization technique. Defining a B-point external to the robot and using a state-dependent and time-varying transformation, unicycle model can be converted into two simple integrators. As a consequence, the state vector of the linear system is the two-dimensional position of the B-point. Notice that there is a potential singularity in the transformation matrix that can be avoided by choosing the B-point at a sufficient distance from the robot center. Finally, we derived a discrete time linear model that has the advantage to exactly describe the robot motion. Unfortunately, this model presents time-varying input constraints, as it will be shown in the next slide. In fact, there are some physical limitations to be taken into account. Angular wheel velocities are subject to symmetrical saturation constraints. These constraints define an axis-aligned rectangular region to which the control inputs must belong. This region is subject to affine transformations when unicycle and linear system inputs are considered. Specifically, the static transformation from differential drive to unicycle inputs will produce the blue region. Furthermore, the second transformations, introduced with feedback linearization, will generate the orange rhombus-like region that for each time instant depends on the state variable theta. The control problem considered in this paper is the following. Given an initial and the target configuration pose, and given the current obstacle-free region for each time instant, the goal is to find a state feedback control strategy capable to fulfill obstacle avoidance, input constraints, and stability requirements so that the robot is driven from the initial position to the target one, irrespective of any admissible obstacle scenario. Some assumptions have been made. First of all, the robot is equipped with a perception module capable of detecting obstacles within a finite vision radius. Furthermore, the robot is equipped with a path planner in charge to generate a sequence of feasible waypoints within the vision radius. In order to be considered admissible, each waypoint belonging to the sequence must fulfill the viability conditions. First, it must belong to the current obstacle-free region. Second, it must be located at a minimum safe distance d bar from each obstacle. And third, each waypoint and its next one must be at most at the distance d bar from each others. These conditions ensure the existence of a circumference centered in each waypoint that does not intersect any obstacle and contains the previous and the next waypoint of the sequence. In principle, an admissible solution to the problem can be achieved via this constrained optimization problem. This semi-definite programming minimizes a quadratic cost under several constraints. The control move at time k plus j must belong to the theta-dependent inputs region, and the j-step ahead state prediction must belong to the obstacle-free region. However, several drawbacks arise in this strategy. In fact, the vision radius r is not infinite, and the feasible input region is not available even for small values of prediction horizon length. Then, we derive the linear and convex formulation of the RHC solution. Given a generic waypoint Zi, by solving this constrained optimization, it is possible to compute an ellipsoidal control invariant set that belongs to the obstacle-free circumference and includes the current robot position and the waypoint Zi. Furthermore, the control invariance property of the region ensures the existence of a state feedback control law capable to drive the robot toward the waypoint with respect to the current input constraints of the system. Notice that the time dependency of the matrices refers to the fact that at each time step k, these variables can be updated without switching to the successive waypoint. However, to solve the optimization problem shown in the previous slide, the feasible input region must be an axis-aligned rectangle. Unfortunately, this hypothesis is not true by a feedback linearization approach. In fact, as it is shown in the left figure, the feasible inputs region is a rhombus-like set that rotates in the plane as long as the variable theta is varying. It is possible to overcome this difficulty by resorting to the computation of inner axis-aligned rectangular approximations. In the proposed solution, at the first time step, a conservative approximation of the input constraint set is computed by using the worst case of inner approximation constraints in order to ensure the recursive feasibility of the optimization problem. Then, for each time k, exploiting the real-time information about the robot orientation, a less conservative approximation of the input constraint set is computed. Here, the modus operandi of the proposed control strategy is shown. Notice that for a generic waypoint Zi, at the first time instant, the red ellipsoid is generated. Then, for each successive time instant, a new blue ellipsoid is computed by adding a further constraint that specifies the inclusion of the blue ellipsoid in the red one. But since the red set is computed with reference to the worst-case input constraints approximation, then the recursive feasibility property is guaranteed, ensuring the existence of a solution for the optimization problem. As a result, for each waypoint, the generated control invariant sets are nested. Furthermore, the viability conditions, previously assumed, ensure the existence of a control law that drives the system trajectory from a waypoint to the next one toward the target. A waypoint switching procedure is performed under the requirement that robot constraint satisfaction and recursive feasibility property are preserved. Let me call sigma the red largest ellipsoidal control invariant region inscribed in the black obstacle-free circumference centered in the next waypoint. Let epsilon be the difference between this circumference and sigma. Then, a safe switching to the next waypoint can be performed once the robot has reached the current waypoint with a certain tolerance equals to epsilon. The proposed control strategy has been validated by means of laboratory experiments performed on a real differential-drive robot known as IEEE. For these purposes, a control architecture has been developed on separate logical modules aimed at carrying out the tasks of localization, mapping, motion planning and motion control. Specifically, an odometry-based localization process is simultaneously executed along with the mapping task. Perception and navigation modules communicate with the robot by using two separate communication channels, respectively a Wi-Fi and a Bluetooth connection. The Choose and Vision module is an omnidirectional camera capable to capture 360-degree images of the environment using a standard CCD coupled with a parabolic mirror. A geometrical model of the omnidirectional system, once properly calibrated, allows to associate a point of the space to each pixel of the captured pictures. Each image is processed in order to extract relevant geometrical information of the environment. Here, execution of image processing algorithms is shown when the robot is located in a rectangular shaped room. First, a distorted image is captured with the camera and is converted into a grayscale one. This facilitates the execution of a Kenny filter capable to detect all edges in the picture. As a result, a binary image is produced, in which each positive pixel denotes a point on obstacle edges. Using the geometrical model of the omnidirectional system and an interpolation algorithm, it is possible to undistort the original image. Although the body of the camera is still visible, knowing its pixel coordinates, it can be easily removed from the scene. Finally, each extracted landmark is mapped into the word frame. Then a geometrical parametrization of all landmarks is computed. A path planner unit has been implemented by resorting to the probabilistic roadmap algorithm. Specifically, given a generic obstacle scenario, the planner proceeds into two phases. In the learning phase, a finite number of points are generated in the obstacle-free region. These points are generated at a certain maximum distance, so-called bar D, from each other, and at a minimum distance, bar D, from any obstacle, in order to fulfill the viability conditions of waypoints. This can be done by using an expansion algorithm for each obstacle. In the query phase, on the other end, a graph is built using the points previously generated. Then the Dijkstra algorithm provides the shortest path from the current position of the robot toward the target point. Notice that only the waypoints belonging to the vision radius are used. The effectiveness of the algorithm is tested by considering an environment with two barrier-shaped obstacles, in which the robot is free to move. For the sake of completeness, the geometric parameters of the robot are reported. Each wheel has a radius length of 2.05 cm, a wheel's axis of 5.33 cm, and a vision radius of approximately 50 cm. Furthermore, the saturation constraints are considered. Each wheel cannot exceed an angular velocity of 6.31 radians per second. This picture shows the joint actions performed by Vision Module, Path Planner and Control Unit. It is possible to appreciate the capability of Vision System to rebuild the obstacles and the determination of a sequence of waypoints that fulfill the viability conditions. Notice that waypoints are tracked one after the other by ensuring that the robot keeps within the guaranteed obstacle-free circumference centered in each waypoint. It is also shown that the prescribed constraints on the left and right angular velocities are always satisfied. Finally, we present a demo of the performed experiment that confirms once again the results achieved. The robot starts to collect information about the environment and simultaneously generates waypoints within the vision range. In the video, the obstacle-free circumferences are visible. As it has been previously discussed, all circumferences are intersected and they represent a feasible path from the initial point to the target one. In conclusion, in this research, a novel receding horizon controller for wheel differential drive robot has been presented. The proposed control architecture combines feedback linearization argument and set theoretic ideas to address constrained reference tracking problems in a priori unknown static obstacle scenarios. Feasibility and closed-loop stability have been formally proved. Finally, laboratory experiments with the IEEE robot have shown the applicability of the proposed strategy. Thank you for your attention. Any question?